Welcome to part 2 of this stress transformation video. In this problem, we are going to be solving just the last part, which is to solve for the point loads labeled P1 and P2 on the beam. So we are given the cross section, we know what it looks like. We want to map those four, we want to make a cut through our section that we're interested in, which is shown, which was where point A is located. And we want to find the internal forces there so that we can kind of figure out what stresses are acting on point A and then go back and solve the forces. So I'm going to redraw our section down here, and then I'm just going to move our forces. You can either find the reactions at the bottom and then move those up to where and then figure out what your internal forces are. I'm not going to go over each and every part of that, but you have to move the forces and figure out the forces that are acting, the forces and moments that are acting at our cross section. So if you didn't see, this is from part 1, all of our stresses that we figured out. So this is going to be our part 2. So we're going to be finding P1 and P2. Alrighty, so here's our cross section redrawn. We can see it's in the X and Y axis. If you look above, you can see where the X and Y axis are currently. We've kind of rotated the cross section so it's a little bit easier to see. But right off the back, you should be able to tell that there's going to be an axial force of compression that's acting on this section, and then there's also going to be a shear force due to point 1. So we'll draw those on our section first. So the first one, we're going to have an axial force. I'm going to draw that as this. It's going into the board, kind of, into the paper. That's a value of P2. And then we also have a shear force that's acting in the negative x direction. That is a value of P1. So moving these forces to this cross section, it's going to cause some moments and possibly some torsion. I think in this case we don't have any torsion. So we're going to cause some moments by moving these two forces. So by moving our P2 force over the cantilever distance of 2 feet, we get a moment that acts in about this axis. So this is P2 times our 2 feet. And then we also get another moment from moving our P1 force down from the top of the cantilever to our cross section. It's going to be about the same axis, just in the opposite direction, and a value of P1 times 4 feet. So those are all our internal forces that are acting on our system. So I'll go ahead and put in some distances on here just so we know. So this is a value of 7 inches. This is 6 inches. And our point A is located 1.5 inches below the top. So now that we can see what kind of stresses are acting on our point 1. So we can obviously see that there's an axial force, so we know we have axial. There is a shear force acting on it, and since our point A is not located at the two ends of it's acting somewhere in the middle, in between, we're going to have a shearing stress. We're not going to have any torsion, so we can cross that one out. And then we have two moments, both applied about the same axis, and since our point A is some distance away from our neutral axis, that means we're going to have some bending stresses. So that means we're going to have 2 normal stresses that are acting on our point and 1 shear stress. So we'll go ahead and start with our shear stress. So the equation for shear stress, in this case our subscripts are going to be Zx because the normal plane to this cross section is the z-axis, and the second point, our shear stress, is acting in the x direction. So our equation for that is just Vq over It. So we have our shear force, we know it's P1, the values, we just are going to be solving for P1. Our Q in this case, we're interested in this area, the area that cuts through our point, times the distance from its centroid to the main centroid. So that leaves us with our Q is just going to be equal to a value of 1.5 inches times 7 inches. That's our area of the section that we're interested in possibly breaking off. And then the distance between those two is going to be 3 inches minus 1.5 over 2. So 3 inches is the distance from the centroid to the edge of our section, and then 1.5 divided by 2 is the distance from the edge to the centroid of the small area cross-section that we're interested in. So that's going to get us a value of 23.63 inches cubed. We also need to find our I value. So our I for this cross-section is just 1/12 BH cubed. So our B in this case is 7 inches. And then our height is 6 inches cubed. So that gets us a value of 126 inches to the fourth. And then our T in this case, our thickness, is the length of the cut we made to make our Q. So in this case, our T would be equal to 7 inches. So now we can go ahead and plug all those values in and then solve for our P1 force. So we know that sigma xz from the stress state above, we know that that's a negative 40.2. So that's going to be equal to P1 times our Q, which is equal to 23.63. Our I value is 126 inches, and then our T is 7 inches. So that gives us a value for P1 that is equal to 1,500 pounds. So that checks off our shear force, so that we've now found our P1 force. Now the only thing left to find is our P2 force. So we can find that based off of the normal stress that's acting on point A. So we know that value. So if we go down here, our normal stress, sigma zz, we know that that is equal to 238 psi. So our equation for our bending stress, sigma zz, that's just going to be equal to our axial stress, which is going to be equal to P over A, plus our bending stress, which is My over I. So let's start to put in some variables. So we know our P is going to be P2, and then we'll have to calculate our area. So let's do that right now. So our area for this piece is just going to be equal to 7 inches times 6 inches. So that's going to get us a value of 42 inches squared. Our Y in this case is going to be equal to our centroid, which is at 3 inches, minus the distance away from the edge of the section that A is. So that's going to be minus 1.5. So that means that our Y is 1.5 inches. So we also need to take into account whether these forces, the direction they're associated with, will cause tension or compression in order to figure out if they're going to be positive or negative, since we have two different stresses adding together. So since we know that our axial force is acting in compression, we know that the axial stress is going to be negative overall. So I'm just going to tack on a negative to our P2 force. So we get a positive value for P2 at the end. And then that's going to be over an area of 42 inches squared. So that we're going to add our moment. So we have two different moments. So we have to consider which one is acting in a positive way and which one is acting in a negative way. So this force caused by our P2 force, that one, if you use the right hand rule, it's going to be pushing into the page where point A is located. So that means this causes a compression on that side. And then the other force, since it's acting in the opposite direction, when you use the right-hand rule on that, it causes a tensile force. So using that, we can say, okay, our moment in this case is going to be P1, which we know, we're going to plug that value in, times 4 feet, which we'll have to convert to inches, so 4 feet times 12. That's subtracted by P2 minus 2 feet times 12 to put it into inches. That's going to give us our overall moment. It's figuring out if it's in positive or negative. So that is going to be multiplied by our 1.5 inches, and that's all over our I that we had calculated, which is 126 inches to the fourth. So all we have to do is plug in our P1 value into our equation and then solve for P2. So when you do that, you should get a P2 value that is equal to 2,000 pounds. And that's how you solve for both of those forces.